Welcome to our discussion of functions. If there's a specific topic you want to review, just fast forward the video until you see this slide with that topic in bold letters. Let's begin with some definitions. A function really is just a relationship between two variables, x and y. X is normally our independent variable and y is our dependent variable. Independent variable is a fancy way of just saying the input. Dependent variable is just a fancy way of saying the output. Something like this is just saying that every time you give it an input value for x, it's going to multiply it by 10 and spit out the answer. So you can think of a function as kind of a question and answer machine. You start with an x, you throw it into this function, it does something to it, spits out an answer. In this case, it takes that number and it multiplies it by 10. That's a function. Now, in order for something to actually be a function, right, there's a difference between a function and a relation. A relation is just being able to relate x and y with some equality or inequality, some sort of symbols. A function has this special extra, one little extra caveat that just says every time you give it an x, you're going to get one and only one y. So every time you take an x and plug it into the function, it's only going to spit out one y. You can give it a second x, and that can give you the same y, and that's okay. And in fact, you can give it a third x, and it goes the same y. And in fact, every x can go to the same y, and that's still a function. It's actually called the constant function. So y equals 3 is a version of a constant function, right? Because no matter what x is, it still just says y equals 3. The problem, or I should say the situation where it's not a function, is when x comes in, goes out to this y, but also goes out to that y. That would not be a function. So you give it one input, it gives you two answers, right? Think of it as question and answers. You ask it a question, it goes, well, I think maybe it's this y, y1, but then no, maybe it's y2. And that's not a function. A function has to be definitive. You ask it a question, it gives you one and only one answer, right? You give it an input, it gives you one and only one output for that input. All of your answers don't have to be different, as we've seen with the first example, but you can only get one answer for every single question. That's what makes something a function. Some of the notation involved, you'll see this a lot, f of x. That's how it's read, f of x. Sometimes people say f at x, but it's really f of x is the more common terminology. That just means a function in terms of x. X is going to be your input, or your independent variable, right? And the output is going to be your function f. So f of x normally takes the place of y. Instead of saying y equals 10x, we now say f of x equals 10x. Sorry, that should be 10x, right? Means the same thing. It's now a function instead of just an equation or a line, right? They don't also have to be f all the time. G of x is also a function, right? H of x is a function, both in terms of x. And they also don't have to be x. You can have f of p. This is now going to be something like y equals 3p minus 5. That's still a function. It's a straight line, except instead of x's, we want to call them p. Remember, p, maybe p stands for price or something. So the variable on the inside of the parentheses just tells you the letter that we're going to use for our independent variable, and then the letter on the outside of the parentheses just tells you the name of the function. And the only reason why we would go from f to g to h would be if we had more than one function that we needed to talk about at the same time. We couldn't call them both f of x. That'd get too confusing. So one would be f of x, the other would be g of x. Okay? Different ways that we can define a function. We can define it by just listing out its ordered pairs. That's a pretty useless way of doing it, and it only works for functions that have a very small finite number of ordered pairs, just a few dots here and there. Doing it with tables is slightly better, but still a problem because it's pretty much just the same thing as ordered pairs. You just put it in a table. So again, it better be a small finite number of things. The two better ways of describing it is with its graph or its equation. The graph is nice because we're visual creatures and we love to see pretty little pictures, and then equations are nice because they're the things that we can actually manipulate and work with and do some math. Here's an example of a couple ordered pair things, and like I said, it better be a small set of ordered pairs for this to work. The domain and range, something that we didn't talk about on the previous slide, but the domain are just all of the possible allowable values that can be put into your function. So all the different values that x, right, your independent variable, can take on. And then y are just all of the possible answers, outputs that you get from your function. So with the first example, r, you can see that you've got a -1, a 1, a 5, and a -1, right, as your input. So there's your domain of -1, 1, and 5. You don't list the -1 twice. The range are all the outputs of 2, 3, 2, and -3. Again, you don't list the 2 twice. And it's not a function because two ordered pairs have the same first component. Yeah, fine. So let's memorize another rule. What does that really mean? It means it fails that first pictorial test. Because if -1 is my x, then this function takes that x and first spits out 2, right? -1 went to 2. But then later on, you put -1 into it, and it also spits out -3. So that's not a function. You can't have two different outputs for the same input. What about the second one? -2, 0, 2, -1, that would be your domain. And 1, 2, 1, -1, so basically just -1, 1, and 2 would be your range. Is it a function? Do we have any problem with the same input going to two different outputs? And hopefully you can see pretty clearly that no, we're fine. It's a function because we don't even have the same input twice. And that's what it's talking about here. How about looking at some equations to figure out if they are functions or not? So in the first example, we basically move some stuff around because we're trying to get it into the form of x equals some stuff or y equals some stuff. So that's why we added the 3y and subtracted the 12 to both sides. So we brought the 12 over basically and the y over the other side. Divide everything by 3, and now we have it in our more standard form of y equals some things, right? So y equals some stuff. Now you can plug things in for x and see if you get more than one answer. Or you can try graphing it, things that we've learned in other videos, and see what happens. In this case, the second one, again trying to isolate y, we move the x squared right to the other side. The 4 is already over there. And then we're left with y squared equals some stuff. So we need to take a square root of both things. This is a problem because now we have two different values of y that correspond to each value of x. And in fact, before you even take the square root, you could see that. If you let x equal 0, right, when x equals 0, you get y squared equals 4. So y equals 2 works, but so does y equal -2. So that's not a function. And in fact, if you remember from one of our previous slides, what does y squared minus x squared equals 4 look like when you graph it? Well, if you don't remember, graph it and you'll see. Okay, evaluating a function is just a fancy way of saying plug in some values for x and see what you get. Here's an example where our function is g. Remember, I told you it doesn't have to always be f. This is a g function now. Who cares? It's just a different name for it, right? So g of 3 just means plug in 3 for x. So you square it, have -6 times it, then add 8, and there's your answer of -1. And you can follow the rest as well. So evaluating functions just mean put in the number for your x. Now D and E are going to be a little interesting. So here's D. When we're doing g of a plus 2, you're putting a plus 2, that entire quantity, in for every single x. You see how that's what x was, that's what x was? What I like to tell my students is think of this function as some buckets, right? You've got this bucket here that's being squared minus 6 times this bucket or box, whatever you want. And then now you're going to put things in there. So if I put a plus 2 in here, the whole thing's getting squared. If I put a plus 2 in here, the whole thing's getting multiplied by -6. That's what the parentheses do. It reminds you that everything's being put into that x. So it's like you're putting everything into a box or everything into a bucket and doing whatever you need to do to that. And then it's just a matter of doing the math slowly and not making any mistakes. FOIL out your a plus 2, distribute your -6, combine all your like terms, simplify, and there you have it. Same thing, except now instead of a plus 2, you just have it with 2 different letters. It's not going to really change anything as far as what you're doing. It's just now you're going to have more letters. So don't panic. It's the same idea. The whole thing gets stuck in for x, right? So the whole thing gets squared. So there is your square of this piece. And then -6 times everything. You distribute the -6 across both pieces. Add like terms. There's nothing here, right? There are no like terms in this case, so it's even easier. Finding the domain of a function, well, that's pretty easy. The domain of a function always starts off with all real numbers. We always start with the largest possible set of numbers, which in this case is always all real numbers, and then we whittle it down depending on the types of functions we have. And there are really only 2 things we have to worry about with functions. There's 2 things that we can't do, and you might already remember one of them. We can never divide by 0, very good, and we can never take an even powered radical, right, like a square root or a fourth root of what kind of number? Negatives. So those are the only 2 things we have to worry about. Whenever we have functions that involve fractions, so our first example, f of x, we have to worry about the bottom can never equal 0. So we start with a domain of all real numbers, and then we just take away those numbers that make the bottom equal to 0, because we know that that's not allowed. So in this case, you would take 1 minus x squared, set it equal to 0, and that would give you 1 equals x squared, right, when you add x squared to both sides. And then you get plus and minus 1, right? If you have either negative or positive 1 in for x, that's a problem. So your domain would be everything except those numbers, and this is how you could write it a couple different ways, right? You can just spell it out. It's the set of all x's such that x does not equal -1 and x does not equal 1. Or you kind of do it in interval notation. It's all numbers from -infinity up to -1, not including, that's why it's a round bracket, union with everything from -1 up to 1, union everything from 1 up to infinity. The second example, right, the square root of x, as we said, we can't have negatives in a square root. So that's just going to be all x's such that x is greater than or equal to 0, right? X such that. One way of writing it, if we want to write it in interval notation, wouldn't it just be square bracket 0 to infinity? There you have it. The C, this one, Again, what's our problem with this, or what's our potential problem with this function, is that we can't have 0 in the bottom. So what values of x would be a problem there? And you look at that and go, well, we just can't let x be 1. So there's that problem. But then you also have the problem of we can't have negatives. So not only can the bottom not equal 0, it can't be less than 0. So what you're really doing is saying x minus 1, right? Everything that's inside that radical has to be greater than 0. We know normally we can let it equal 0 for a radical, but we can't let it equal 0 here because it's in the bottom of a fraction. So that tells us x just has to be greater than 1 when we just add 1 to both sides. And that's what they got. And then the last one. Well, for part D, are there any fractions, right? Are there any variables in the bottom of a fraction? No, because even if this last number were a fraction, or even if this was, 2/3 times t, it's still not a problem because we don't have t in the bottom of a fraction, right? There's no possibility for any of those fractions to have 0 in the bottom. So there's no possibility that it can ever be divided by 0, so we don't have to worry about that. And there aren't any square roots anywhere, so we don't have to worry about those. So what is the domain of that one? Well, what did we start with? All real numbers. So all real numbers. And the negative infinity to infinity is the easiest way to write it, unless you want to write just a capital R with 2 lines. That's the symbol for all real numbers. Identifying the graph of a function, right? So basically, if you're given a graph, can you identify whether or not it's a function? And that's very easy. If you remember, you probably already remember this. It's the good old vertical line test. So anytime you're given a graph, you just draw a vertical line, and if anywhere on that graph a vertical line touches it in more than one place, it's not a function. Because if a vertical line touches it in more than one place, that means you have 2 ordered pairs where you have the same x value but different y values, and that breaks the rules of what makes something a function. We can see that this one obviously fails miserably everywhere, right? Because every vertical line around here is going to have 2 values. So that's a problem. What about if we had a graph that was just a bunch of dots? Well, then you'd have to see, do any of them line up, right, vertically on top of each other, and you'd see that these two are a problem. So that's not a function. How about this one? Now a vertical line hits it in 3 places. Even worse, not a function. What about this one? Well, if you take a close look at it, even though the sides, right, the edges of it are getting fairly vertical, they're not perfectly vertical. Right? They're still going up at an angle. So that one's fine, passes the vertical line test, that's a function. How about that one? Again, the lines are getting very close to vertical, but they're not vertical, so it's a function as well. If we're given an equation, we can also figure out if it's a function by first graphing it. So just have whatever techniques you normally have to figure it out. This question is actually asking a bunch of things first. First, it asks if that point is on the graph of that function, which is a fancy way of just saying, does that point satisfy that equation? Plug in 1 for x. What do you get? 1 squared minus 2 minus 3. And that equals -4, which is not -3, so no, it's not a part of your function. Find all values of x such that x comma 5 is on the graph. So that basically just says, if y equals 5, what does x equal? Well, that's what we're doing here. We plug in 5 for the output, right, for our y value. Then we move it over, because the only thing we can do with quadratics is we can only set them equal to 0 and solve. So we move the 5 over, now it's equal to 0, we factor it, we solve, and we get the 2 values, 4 and -2. So is this a function? Because we have 2 different values going to the same, so we have 2 different inputs going to the same output. Is that okay? Is that still a function? Yes, it's when we have the same input going to two outputs. That's a problem, right? Here we've got two different inputs going to the same output. That's fine. Okay, find all y-intercepts of the graph. Well, y-intercepts are when x equals 0, so just plug in x equals 0. Simple. Find x-intercepts. Well, that's when y equals 0, so you set equal to 0. Factor and solve. Also not too difficult. That's all the stuff we needed to do for graphing a function from its equation, because once we have all of those information, all those bits of information, we could plot all that and then graph that function pretty easily. Okay, finding the average rate of change of a function. Well, average rate of change is a fancy word for a straight line that connects two dots. If I have a function that looks like anything, doesn't matter what it looks like, curvy or whatever. So let's say this is my function here. Kind of looks like a straight line, right? Let's say this is my function like this. Doesn't matter. Let's say my function looks like this or like this. It doesn't matter what it looks like. The average rate of change of the function is just saying pick 2 points. 1, 2. Now go up to your function. You choose the red one here. And the average rate of change is just the straight line, the slope of the straight line that connects them. And how do we find slope? If you remember, change in y over change in x. Right? Slope is change in y over change in x. Or if you remember the function, or the full equation for it, y1 minus y2 all over x1 minus x2. Remember that? Well, what the heck does all this mean? Well, look up here. This is a and f of a, b and f of b. Isn't this just x1 and this is x2, right? And then what is f of a? That's the output you get from your function, which is the same thing as y, and this is y as well. So if you do the substitutions down here, this is just y2 minus y1 all over x2 minus x1. It's slope. So it's just the slope of the line connecting those 2 points. If this was a, that's an a, sorry, and this is b, then here's a point, and then there's the other point on the red line. That slope connecting those two is the average rate of change of the function over that interval from a to b. Actually, a pretty important concept. That's the first thing we use to teach derivatives in calculus. So make sure you understand, average rate of change is just the change in y over change in x over an interval. Finding the average rate of change is very simple. You're given the a and the b. All you have to do is plug each of those into the function and get the 2 corresponding outputs, right? So you're basically given 2 x's called a and b. You plug them both in and get 2 y's called f of a and f of b. And then use that fancy formula, which is just another formula for slope, and calculate the slope between those 2 points. So we're right back to just finding the slope of 2 points. Here's another example. If we're going to go from c to c plus h, so now they're going to make it harder on you. Instead of giving you actually 2 numbers of what's the average rate of change of going from 3 to 7, they say going from c to c plus h. Well, you plug in c plus h, you plug in c, you do a bunch of messy algebra, and you end up getting 4c plus 2h. Just like before, you got to remember that when you're plugging in c plus h, that whole thing, right? That whole thing of c plus h goes in for x. So all of it gets squared, which is what this is, right? That's squaring out c plus h. That's kind of foiling out that c plus h. And then when you plug in c, right, it's just c gets squared. Combining like terms, make sure to distribute your minus sign, bop, 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 you get this stuff. When you get down to the bottom, C plus H minus C, of course the C's cancel, you just have H on the bottom. And on the top, the 3's canceled, the 2C squareds canceled, and everything that was left over had an H in it. So you could pull that H out, right? You could factor out an H on top, and then those two things end up canceling, and that's why you're left with just 4C plus 2H. Last but not least, solving some applied problems. The first one we've already seen, this idea of x plus h, right? F of x plus h minus f of x all over h is called the difference quotient. We just did that with c, the c plus h. Isn't c plus h and c the same thing as x plus h and x? Just replace the c's with x's. So finding the difference quotient is the exact same thing we just did. First thing they did is they evaluated f of x plus h, got that big long polynomial. Then you subtract f of x from it. Very simply, that's all of that ugly stuff, right? So that first set of parentheses, that's the f of x plus h that they found. Then they're just subtracting the original f of x from it. You can see that that's going to get rid of this piece, and this piece. And now, I'm going to skip down here, look what's left. Just these pieces, right? On the bottom is just h. What do you notice about all the pieces that are left? They all have h in them. What do you remember about that last example we had? After we canceled out like terms, didn't we also have something left where each piece had h in it? Well, here's the nice little secret, is whenever you do a difference quotient, as long as you do your algebra right, you're always left with nothing but pieces with h's in them. What I'm saying is the h will always cancel in the end, right? You'll always have something left with an h in each piece, so you can factor that h out and cancel it. If you don't, like if you're left and one of your pieces doesn't have an h in it, you mess something up. It has to cancel. This has to work. So that's a good check to figure out whether or not you messed up, because this can be difficult doing all this stuff up here, putting x plus h in for x and making sure you're squaring it properly and doing all those things. So just take it slow. Remember, you're putting something into a box, so everything's being acted on that. So all x plus h, the entire quantity is being squared, the entire quantity is being multiplied by 2, etc., etc. So here is your final answer for your difference quotient. Also, very important, because that's the beginning of the definition of a derivative. The next thing you do is you take the limit as h goes to 0, and all of a sudden you have the derivative of your original function. Here's another example. Bioavailability is the amount of a drug you have ingested that makes it into your bloodstream, right? Because when you take it in, it's getting acted on in your stomach, and so not all of it's going to get into your bloodstream. A statin with a bioavailability of 30% has been prescribed for Boris. Boris is to take 20 milligrams of this statin every day. During the same day, 1/2 of the statin is filtered out of the body. Find the maximum concentration of the statin in the bloodstream on each of the first 10 days of use and graph the result. So since it has a 30% bioavailability and he takes 20 milligrams per day, the maximum concentration in the bloodstream is 30% of 20 milligrams, or 6 milligrams from each day's prescription. But because 1/2 of it is filtered out each day, the daily maximum concentration is going to be 1/2 of the previous day's amount plus 6, right? So think about it this way. He takes a pill and he instantly has 6 milligrams in his body. At the end of the day, 1/2 of it goes away, so he's left with 3 milligrams. And then he takes his next pill, which adds another 6 milligrams to it. So now he has 9. At the end of that day, half of it goes away. He now has 4.5. And then he takes his next pill. And the pattern keeps repeating. Here's what I just showed you, but worked out a few more steps. So there's the first day of 6. Remember, then it went to half, which was 3, added 6, got 9. Went to half, which was 4.5, added 6, which got you to 10.5. Take half of that, add 6, keep doing that over and over and over again. And there is the function representing the amount in his bloodstream. Okay, so those are some examples of functions that are modeling things that happen in the real world. And that's it for our discussion of functions.